Good morning, everyone. Imagine you're riding your motorcycle home. After a few minutes, your helmet becomes hot and uncomfortable. Now imagine that at the same time an accident occurs. Besides the direct impact, your head may also experience a sudden rotational motion, increasing the risk of serious brain injuries. This situation shows that although helmets are designed to protect riders, there are still important challenges that need to be addressed. Today, our group will present an innovative solution that applies the principle of rotational mechanics and thermal physics to improve both rider safety and comfort. The key need we aim to address is the need for a helmet that not only protects riders during accident, but also reduce heat build-up inside the helmet, making it safer and more comfortable for daily use. Conventional helmets provide basic protection against direct impacts. However, they do not effectively address excessive heat inside the helmets or reduce the rotational force that may occur during a collision. These problems are experienced by many motorcycle users, especially daily commuters, food delivery riders, police officials, and long-distance riders. They wear helmets for extended periods and are frequently exposed to hot weather, traffic congestion, and road hazards. Therefore, improving both comfort and safety is essential for these users. From the perspective of thermal physics, sunlight transfers heat to the helmet through radiation. The heat then moves from the outer shell to the inner padding through conduction. Because conventional helmets have limited airflow, convection is less effective, causing hot air to remain trapped inside the helmet. From the perspective of rotational mechanics, during an accident, a force acting away from the center of the helmet creates torque, causing the head to rotate suddenly. This relationship can be represented by the equation T equals R multiplied by F, where T is torque, R is the distance from the center of rotation, and F is the applied force. This rotational motion may increase the risk of traumatic brain injuries, even if the helmet absorbs the direct impact. If these problems are not addressed, riders may continue to experience discomfort, excessive sweating, fatigue, and reduced concentration while riding. More importantly, rotational motion during accident may increase the severity of brain injuries, resulting in higher medical costs and greater safety risks. Therefore, there is a clear need for a helmet that provides better thermal comfort and improved rotational protection. To solve these challenges, our group has developed the Smart Adaptive Cooling Helmet, an innovative design that combines the principle of rotational mechanics and thermal physics to provide better protection and greater comfort for motorcycle riders. Now, I would like to invite the next member to explain the design and innovative feature of our proposed helmet.
Now I will explain the innovations of this smart adaptive cooling helmet. Main problem we're trying to solve is heat buildup inside the helmet. To solve this problem, our helmet is equipped with several smart components. First, it uses a temperature sensor to continuously measure the temperature inside the helmet. Next, a humidity sensor detects the amount of moisture caused by sweat, allowing the system to monitor both heat and humidity levels. The sensor data is sent to the microcontroller, which acts as the brain of the helmet. It analyzes the reading and decides when cooling is required. If the temperature rises above a preset value, the mini cooling fan automatically switches on to increase airflow and improve ventilation. For extremely hot conditions, the Peltier cooling module provides additional cooling by transferring heat away from the user's head. The entire system is powered by a rechargeable lithium-ion battery, while Bluetooth connectivity allows users to monitor the helmet through the smartphone application. An optional solar panel can also recharge the battery during daylight, making the helmet more energy efficient and environmentally friendly. These innovations make the helmet intelligent, comfortable, and suitable for real-life applications such as motorcycling. Next, let's move on to the mechanical designs of this helmet. This helmet is designed with both protection and cooling efficiency in mind. The outer shell, made from ABS plastic or polycarbonate, provides high impact resistance while remaining lightweight. Beneath the shell is the EPS foam liner, which absorbs impact energy during an accident to protect the user's head. Soft comfort padding improves the fit of the helmet and absorbs sweat during long periods of use. At the top of the helmet is the cooling chamber, which contains the cooling fan, Peltier module, and the heat sink. The helmet also includes specially designed air duct channels that guide cool air around the user's head. As shown in the airflow diagram, fresh air enters through the front and chin vents. The cooling fan pushes air through the internal air channels, allowing it to absorb heat from the user's head. The warm air is then expelled through the top and rear vents, creating continuous air circulation inside the helmet. This process demonstrates the physics principle of forced convection, where moving air removes heat much faster than still air. The electric component safely houses the lithium-ion battery, microcontroller, temperature sensor, humidity sensor, and wiring, which ensures the system operates reliably while remaining compact. Overall, this mechanical design combines smart engineering and fundamental physics principles to provide cooling and improves user support while also maintaining safety in hot environments. So how does the cooling system operate? The cooling system operates automatically using a closed-loop control system. When the helmet is switched on, the temperature and humidity sensors continuously measure the conditions inside the helmet. The sensor readings are transmitted to the microcontroller, which compares the measured temperature with a preset value. If the temperature remains below the preset limit, the cooling system stays off to conserve battery power. However, once the temperature exceeds the threshold, the microcontroller automatically activates the cooling fan, which increases the airflow around the user's head. If the temperature continues to rise to a higher level, the Peltier cooling module is activated. This provides additional cooling for extreme environmental conditions. Once the temperature returns to a comfortable level, the cooling device is automatically switched off, making the system both energy efficient and fully automatic. This smart adaptive cooling helmet applies several important physics principles. The first principle is heat transfer. Heat produced by the human body is transferred from the head to the helmet through conduction. Next, the cooling fan removes heat by forced convection. As the fan pushes the cooler air through the helmet, moving air carries heat away much faster than still air, which improves the cooling effect. The helmet's reflective outer shell also reduces heat absorption from sunlight through thermal radiation, which helps to keep the inside cooler. Another important principle is the Peltier effect, also known as thermoelectric cooling. When an electric current passes through the Peltier module, one surface becomes cold while the opposite surface becomes hot. The attached heat sink and cooling fan remove heat from the hot side and allows the cold side to cool down the air inside the helmet effectively. Finally, the system demonstrates energy conversion. The rechargeable battery stores chemical energy, which is converted into electrical energy to power the sensors, microcontroller, cooling fan, and Peltier module. The fan then converts electrical energy into mechanical energy by rotating its blades and generating airflow. These physics principles work together to provide an efficient cooling system while maintaining user safety and comfort. So let's move on to the thermal innovations.
I will explain the thermal innovation used in our smart adaptive cooling helmet. Our helmet uses phase energy material HPCM, which is special material that absorbs excess heat when the temperature becomes high. During this process, PCM changes from solid to a liquid while storing heat energy. This reduces the amount of heat transferred to the rider's head and helps keep the inside of the helmet cooler and more comfortable. This innovation applies the concept of thermal physics, especially latent heat and phase change. PCM can absorb a large amount of heat without a significant increase in temperature, making it effective in reducing heat buildup inside the helmet. However, there are some technical challenges such as the use of PCM increase the production cost, and the helmet must remain lightweight, durable, and face safety tests while maintaining its cooling performance. Compared to a standard helmet, the smart adaptive cooling helmet provides better cooling helmet, greater comfort, and improved protection. Riders can wear it for a longer period with less heat and discomfort. In conclusion, the smart adaptive cooling helmet provides riding comfort by reducing heat inside the helmet. By applying the principle of thermal physics, it offers a cooler, safer, and more comfortable riding experience. I think that's all from us. I hope you gain knowledge by watching this video. Thank you.